So let's talk about number 23. Were there any others you had questions about besides 23 at the moment? Anything else you wanted to know?
Okay, like, when you do the left one for, like, on 20.
Right.
So you just change, like, that I equals 0, and then, like, the top would be 19, but when you do, like, you have to change, like, inside the parentheses.
You don't. That's the thing. So give me an example. So what do you have for 19? Like you were just talking about C when you had 20 subdivisions. So what do you have for 19C? It was, hang on here a minute. So it was the integral from 1 to 2 of cube root of x dx, right? So what do you have for your sigma there? So it was for 19. So you had 1 to 20, right? And then cube root of on C. 1 plus I over 20. Okay, so that'd be more of a mixed. Okay. Oh, all of it over 20. All of it. I'm with you. I think you would want 1, it would be 1 plus I over 20. Because that'd be 1 and 1/20th, 1 and 2/20ths. Right. So going back, okay, so here's 1, here's 2. If we're going to do, so the width would be 2 minus 1 over 20, right, which would be 1/20th, right? So I'm with you on all that. So this would be 1 and 1/20th, or it'd be 21/20ths. Either way. So if you do 1 and 1/20th, then it'd look like this, right? 1 plus 1/20th, 1 plus 2/20ths, 1 plus 3/20ths. And that's perfectly fine. Matter of fact, sometimes that's a really good hint in a problem. That's what we're going to talk about today, that this started at 1, right? Because if it's 1 plus 1/20th, 1 plus 2/20ths, 1 plus 3/20ths, where must your left edge have been? Your left edge must have been at 1. Remember, that's what the integral tells us. See, because remember today what we're doing is we're going to go from here to here. So we're going to have to figure out what our left edge is and what our right edge is, right? And because that's what these numbers are, is our left edge and our right edge. So if we go 1 and 1/20th, 1 and 2/20ths, 1 and 3/20ths, 1 and 4/20ths, that tells us 1 must have been our left edge, right? When we write it as an improper, like you guys are saying, which is how I've been doing it, which is fine. The only problem with that, so 21/20ths would be 20 plus I over 20 is what you're saying, right? Because that would be 21/20ths, 22/20ths, 23/20ths. Remember what we did with the integrals where we split this apart, right? So if you saw it like this, you could split that apart and you could say, well, that's 1 plus 1/20th, 1 plus 2/20ths, 1 plus 3/20ths. So again, that tells you that 1 was your left edge. Or you could just say, okay, 21/20ths, 22/20ths, 23/20ths. So 21/20ths was your first right edge. That's 1 width over from 20/20ths, or 1. Our left edge must have been 1. So the key is going to be finding our left edge today. But anyway, I'm jumping ahead here a little bit. So something like that, or the other thing you have is fine too, the 1 plus I over 20. Okay, and then times 1/20th out here. Okay, so to answer your question, for number 20, all you do is change that, and you leave for a left, you leave this exactly the same.
Yeah, that's what I had. I just didn't know the change.
And here's why. Because if we let I be a 0, this would just be 20/20ths, the first thing we plug in. So remember, this is height times width, height times width, height times width, right? So let's don't get lost in all the lingo and all the stuff here. Remember, we're doing height times width, height times width, height times width. So this is my first height. Well, what's the first thing I'm plugging in to this function to get that height? Remember, that's what we do. We plug in to get a height. That's what we're doing. So what's the first thing we're plugging in? Well, when I is a 0, the first thing we're plugging in is 20/20ths, which is what? 1, right? Well, where do you start on the left rectangle? What's the first thing you plug in? The left edge, right? The first left edge, which in this integral was 1. So the first thing you plug in is at 20/20ths, right? If you're doing right rectangles, where's the first thing you plug in? If 1 is your left edge, the first right is 1 width over, right? 1 width over. So the first thing you should plug in to get your first height, you should plug in 21/20ths. 21/20 is the first width over, right? 21/20, and that's what you do for a right. Okay, so that's why you always care about what this first thing is here, because when you plug that I in, whatever's where that X is, that's the first thing you'd be plugging in to get your height. Okay? All right. So anyway, long answer, but you don't change anything. To go from a right to a left, you just go 0 to 19. You got it. All right. So let's do 23. So 0 to 5. So here's 0. Here's 5. Right? And we do what? Figure out our width, right? 5 minus 0, 1/2. So the first width over here is going to be 1/2. Next one, 2/2. Next one, 3/2. And then finally, 10/2. Right? Now we could leave it 5/10 if we want, but I don't think when you get your initial width, I think reduce it is probably the way to go. Okay, so we're doing a midpoint. So now we got to figure out those. Right? And let me put in my last one here. This would be 9/2. And then, so my last midpoint, right there. So what's this one? 1/4. What's this one? 3/4. So you got to be careful, because what is your width? If your width is 1/2, it's really 2/4, right? So these red dots are going to be one width apart. So you're going to go, because a lot of people want to go 1/4, 2/4, 3/4. That's not what it is. It's 1/4, 3/4, 5/4, right? You're moving over to go from one midpoint to the next midpoint to the next midpoint. You're moving over a half, one width, okay? And what would be this last one? Well, it'd be between 18/4 and 20/4. 19/4. It would be half a width away from the right edge. It's half a width away. So it's 1/4 away from your right edge. And this one's 1/4 away from your left edge, but all the red dots are 2/4 away from each other. Okay? And that's why I think this, drawing this out helps that make sense. Okay, so my first left, remember what we're doing? We're going up and drawing a rectangle then, right? I mean, that's what we'll be doing. We'll be going up at our midpoint to the curve, and we'll be drawing a rectangle. That's our first rectangle height. So that'll be f of 1/4 times 1/2 plus f of 3/4 times 1/2 plus f of 5/4. With midpoints, I always tend to write a few more just so I can see the pattern. Plus dot, 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 and the last one, you don't have to do the last one, but I always like to do the last one just to make sure when I do my formula that I can plug in that top number, and I can get that last one. It makes me feel good that I got it all like I needed. So what am I going to go? I usually would start at 1, but you don't have to. So I would be 1 to 5. No, doesn't have anything to do with this, right? We talked about that yesterday. These two, that's your left edge and your right edge. That doesn't have anything to do with the sigma. The sigma is how many rectangles how many things are you adding up? We're adding up 10 rectangles. Okay, so we got f of something, and then this is just going to be 1/2, and actually we know that's going to be a 4. The only thing we got to figure out is how do I do 1, 3, 5, 7? How do you do that? You need something plus 2i, right? When you're adding 2 repeatedly, that's 2i. So we need something plus 2i. If I'm going to start I at 1, we better go -1 plus 2i. Now, I like what Max is saying. Why wouldn't it make more sense to just start at 0, right? Start at 0 and go 1 plus 2i. Instead, I have to do a -1 plus 2i. But -1 plus 2, that'll give you 1. -1 plus 4, that'll give you 3. -1 plus 6, that'll give you 5. And the last one, put in a 10, -1 plus 20, that'll give you 19. Sometimes people write 2i minus 1. Okay, whatever. Okay, but start it at 0 and go 1 plus 2i, that's fine. All right, so then the last thing is to just put it into here. So you got sigma I equals 1 to 10. you got square root of, and then you put this in for x, -1 plus 2i over 4 times 1. Okay? What do you think, Emily? Too easy? You got this look on your face like, it's either, what is he talking about? God, this is too easy. Put a voice in my mouth. I think it's that. Okay? All right. So, again, same process. We want to say, so again, what does this represent? Let's not forget the big picture here. Let's just, because I might ask you that, right? I might give you this, and then write this, and say, what does this represent? This represents the area from 0 to 5 under the square root curve. What does this represent? The area of 10, what rectangles? Midpoint rectangles. I might not tell you this. I might just give you this, and give you this, and ask you to tell me what that is. And I would want you, now, what would be the giveaway? Probably the 2 and the 4 right there. To me, would be a giveaway that they're probably midpoint rectangles. Now, I would probably plug in a 1 and say, okay, that plug in a 1, that gives me square root of 1/4. Okay, what do I know this 1/2 is? Height times width, height times width, height times width, right? When you see this 1/2, you think width, right? This is my width, okay? I know I got 10 of them. That's my width. If there's 10 of them and they're a half wide, what's that tell you? If you got 10 rectangles and they're a half wide, what's that tell you? Well, it doesn't tell you it's from 0 to 5 quite, but it tells you, but you're on the right track. No, well, yeah, we're going to assume that. They're the same width, okay? We're not quite there yet. If I got 10 of them, 10 rectangles, and they're all half wide, what's that tell you? She's close. She said it tells you the integral's from 0 to 5. Not quite. It's 5 wide. The total interval that you're looking at is 5 wide, but it might not be 0 to 5, it might be 1 to 6, might be 2 to 7, might be 3 to 8, right? Might be 4 to 9. Well, we know the total width. I'm trying to lead you into where we're going with this today, okay? When you look at this and kind of know something about that. But on the quiz, I might give you this and tell you, okay, then we did an approximation and got this. What is this? I want you to be able to look at this and say, well, it's 10 midpoint rectangles, right? And so what would your thought process be? Well, you got 10 of them. The width, we know this is width because we know height times width, height times width. So this is our function right here, right? This has to be our function. Sure enough, it was square root of x. So our function must have been this. This was the width. So I got 10 of them. They're half wide, so I know the total interval is 5. Okay, when I put a 1 in for I get 1/4. So the first thing I plugged in must have been 1/4. Well, these are midpoints, and they're a half wide. Oh yeah, and then I could create this. I'd say, well, if they're a half wide and the first midpoint's 1/4, what must this left edge have been? 0. And that's when you would then go, oh, okay, the left edge is 0, and I know its total width is 5. This must have been from 0 to 5, right? So where we're headed with this today is we want to take this, and if we didn't even know that, we want to take this and we want to build that and create that. All the information's here that we need, right? We're just going to have to kind of go in reverse, right? Going this direction is pretty easy now. I mean, hopefully, because we kind of know the steps. We go ahead and we just find our width. We kind of make ourselves a number line. We see where they are. We write out each rectangle. We see the pattern. We write our sigma and F notation, and we plug in the function we got. Working backwards is more of a, okay, what do I have? And I kind of piece it together to work it backwards, kind of like what I was just talking about. Okay, but you know what these pieces represent. Width, height. Sometimes that width is stuck out in front, which is fine. If it's out there, we know that's what it is. Okay? All right. So, I want you to understand. I want you to be able to go through the mechanics of this, but I want you to understand what it is that you got here. So this is 10 rectangles. Is this answer the same as this answer? No. This is the exact area. This is just 10 midpoint rectangles, right? It's not going to be exact. So it's going to be an approximation to that. So let's not forget what we're doing. Okay. All right. So We did that yesterday. All right, well, let's jump right into it. Okay, let's jump right into it. So, you guys give this a go. Tell me what integral, just jot it down there in your notes, whatever, write that down. I want you to write down what you think this represents and tell me what integral created that. All right. So, what do you think? What information do you see there?
Starts at 2.
What starts at 0? Why?
Because if you plug in your first point,
Okay. So if you plug in your first I, you get 0 squared. Okay? So why does that tell you it starts at 0? Okay, so to me that's the first thing, right? It doesn't matter. I mean, you know that's good. That's good stuff. But right away the 0 to 9, right? Probably is a tip off. Doesn't have to be, right? Remember, every sigma we can make our rights start at 0 if we wanted to, right? We can adjust them all. I'm not going to try to trick you that way, probably. Okay, but that's what you should do. Is the first thought is, hey, I bet this is a left. This is a left rectangle, and your first one is going to be when I is 0, right? Your second rectangle is when I is 1. Your next rectangle and your last rectangle is when I is 9. So if it's a left rectangle situation, you start at the left edge, right? So that's nice, okay? Because that's one of the things we're trying to figure out, right? We're trying to figure out what is the left edge, what is the right edge, what is the function, and we know we got a dx there, right? So those are the pieces we need. So putting in a 0, seeing you get 0 squared, that must be the left edge. Okay, that's good, because if you can figure out that left edge, that's a big piece of this puzzle. Now, you wouldn't have to do that first. Okay, what else is in there? Okay, now notice I didn't reduce that. Normally we would make this 1/5, and you would write this as 1/5, but then you'd say, geez, if that was 1/5 and this had a 10, you might be thinking midpoint. Well, if you're going to reduce this, you would reduce this too, right? And so probably this would have been 1/5 and this would have been I over 5, right? But that's okay. So I'm not going to probably try to trick you where I would, reduce this but not this. But be careful of that. I mean, you should be aware of that. You should know enough to think it through. I mean, trying to give you some tips. If this is 0 to 9, think left. Doesn't guarantee it's left, but a lot of the times it is. So that's at least a good place to start. Okay, so we're going to have a width of 1/5, right, or 2/10. Let's say it's 2/10. Okay, so what good does that do you? The width is 2/10. Total distance. I always think that's a good thing to know, total distance, because that'll help us get this here, right? So the total distance is 2. Why? Because if the width is 2/10, what else do you need? How many of them you have, right? If you go from 0 to 9, that means you have 10 of them. Well, 2/10 times 10 is 2. So if you're convinced the left edge is 0, then this has to go 0 to 2, right? Now, the other way you could then really solidify that and make sure is put a 9 in, right? Put a 9 in. That's 18/10. Now where would 18/10 be? That would be 1 width, right? Because this would be 20/10. That would be 1 width short of the right edge. Now, here's where people screw this up. Because people think, okay, like Will said, if I put a 0 in here and get 0, that's my left edge. Then people will put a 9 in here and get 18/10 and think that's their right edge. And they will put 0 to 18/10 here. Well, number one, how many times do we see integrals that go 0 to 18/10? Hardly ever. Now, could we? Sure. We could have an integral that goes 0 to 18/10. You could, but hardly ever, right? We don't see that right. So that's number one. But number two, why can't we plug this in to get our left edge and this in to get our right edge? Yeah, no rectangle uses both the left and the right edge, do they? Left rectangles use the left edge but not the right edge. Right rectangles use the right edge but not the left edge, right? So you wouldn't expect to be able to put this in to get the left edge and this in to get the right edge. You shouldn't expect that. The only one that uses both is a trapezoid. And we're not even talking about trapezoids here, are we, with our sigmas? Our sigmas are going to be rectangles only. Yeah, we're just going to do rectangles only. As far as this, going back and forth between sigmas, right? Because we want to go back to that definition, which was the integral is the limit of the Riemann sums, and Riemann means rectangles, right?
Can you do sigmas, trapezoids?
Sure. Yeah, we did yesterday, I think. Did we do it? No, we found a T3. We could. We'd see a pattern, and we could write it. Yeah, we could write a sigma, because there'd be a pattern. So we could do it, but we're just focused on Riemann sums, so just write that. Okay? So we shouldn't expect to be able to plug a 0 in to get the left edge and a 9 in to get the right edge. That's not what we do. We plug a 0 in to get the first rectangle, and we plug a 9 in to get the last rectangle, right? The last rectangle is at 18/10, so that's where your last left rectangle height should be, is 1 width short of the right edge. So you plug a 9 in, you get 18/10. That's 2/10 short of the right edge, which would be 20/10. Oh, 20/10 is 2. So the right edge should be 2. So you can get the right edge either by knowing the total width, right? If you know the left edge is 0 and the total width is 2, then you know it must go 0 to 2. Or you can get the right edge by plugging in your last number. You're saying 18/10. Okay, these are left rectangles. So the last left rectangle should be 1 width short of the right edge. So 18/10 is 1 width short of 20/10, which is 2. So that's why the right edge is 2. Does it make sense? So you can get the left and right edges either way. All right. And then what's left?
The x squared.
The function, right? And the function is it really that simple? Are you sure it shouldn't be like 2x over 10 squared or something? No, you're right. It's the x squared. Because this stuff in here, that's like the German shorthand, right? The messy stuff is what we put in for x, right? So let's go back. I got it. It sounds like you guys are getting this. You guys are doing great. But let's go back to this, okay? Let's look at this and compare it to this, right? Sigma, messy. Integral, it's the opposite of messy. It's clean, right? My daughter's bedroom, right? The normal person's bedroom, right? Messy, clean, right? Neat, clean, whatever. Not messy. Okay? We would expect sigmas to have a bunch of fractions and messy stuff in them, right? Every one we've done has, right? Every sigma we've done has been messy, right? With fractions and all kinds of crazy stuff. The integral's not so much. So this stuff in here, remember, this stuff in here came from our pattern. So this -1 plus 2i over 4, that all was where the x goes. That all is what we would plug into the x. So wherever the messy stuff is on the inside of something, that's your function. That's your x. So you're exactly right. It is simply x squared. So we would expect messy, not messy. So if you're giving your answer and you're putting 0 to 18 tenths. And you've got a fraction squared. No, not good. That's too messy. Integrals are not messy. Sigmas are. I mean, it's not to say you couldn't get a weird function with some fraction. I mean, you could, but not in this case. Because then, if this is a little bit messy, then this is really, really messy here, right? So, you know, just, I guess this is a normal amount of messy. Okay, now, so, anyway, that's what we should expect. So that integral created that right there. Are these two things the same thing? No. This is the exact area. This is 10 left rectangles. Approximation. Okay? All right, do that one. All right, what are you seeing in there? 100 rectangles. Okay? Absolutely. What kind of rectangles? It starts at 1. These match, and this could have been reduced clearly, but then that 5 over 100 would have reduced. So there's a match there, so I would say they're right rectangles. Okay? What else? Why are you starting at 2?
Otherwise, you get 2 plus 5 hundredths, and that's
So you've split that apart already.
Yeah.
So 200 over 100 is 2, plus, and then when you put a 1 in for I, you would get that.
And the width is 5 hundredths, so that's just not good, right?
Since the width is 5 100ths, because of that right here, and when you plug a 1 in, the first rectangle is at 2 plus 5 100ths, and that's what right rectangles should do. Right rectangles should be 1 width over from the left edge. So the left edge must be 2, not 2 and 5 100ths, right? When you plug a 1 in, you get 2 and 5 100ths. That's not your left edge, because they're right rectangles. So the right rectangle should be 1 width over, okay. Or you could have said it's 205 100ths, right, if you plug a 1 in, right? Well, where's 205 100ths? That's 5 100ths. Again, the key is knowing that's the width. It's 5 100ths over from 200 over 100, which is 2. Beautiful.
Which is
The messy stuff in here is where the X was, right? That's like the German shorthand, right? F of German shorthand. Take German shorthand, you plug it in for the function. The messy stuff is where the X was. So the function is simply sine X. It is not a bunch of other stuff. Okay? The dx, well, doesn't the dx just kind of take the place of that, right? Remember how we said that's delta x? We said our, back when we did we had f of c sub I, our thing here, times delta x sub I, right? I mean, that's our function, and that just becomes a dx, because when we do the exact area, how many rectangles do we have? Infinite. And how wide are they? Well, if you have an infinite number of them, they're actually how wide? 0, right? I mean, it disappears. The dx, the width kind of goes away. I mean, remember, we don't actually ever get to infinite, right? We approach infinity. And so this is approaching 0. So that's why this 5/100 just kind of disappears. A lot of times people want to know, where does that go? Sometimes people even stick it out in front of it, right? If I would have pulled, because in the book a lot of times they're going to take and they're going to write this 5/100 over here, right? They're going to pull that 5/100 and put it out in front. Don't bother with that. I like to put it here because I like to think f of x dx. I like to think of this, right? But if they pull it out here, fine. But that doesn't mean you pull it out here, right? You don't put it over here. That becomes the dx, right? That becomes the dx in here because it goes away. Because if you have an infinite number of them, there is no width. So the width disappears. What's left? Goes to 7. And how are you in that? One way is to put 100 in. So you'd have 200 plus 500, which would be 700 over 100, which is 7. And that is the right edge. We'd expect that because these are right rectangles, so right rectangles should go all the way to the right edge. And that is 7. Also, what would be another way? The width of 5/100ths for each rectangle, and you have 100 of them, that's going to be a total width of 5. So if it starts at 2, it's got to end at 7. Total width of 5. Messy. Clean. Neat. Okay. I kind of like that. Kelsey's bedroom. Everybody else's bedroom. Don't tell her. You will. Yours totally is.
Ryan have a bedroom?
Ryan's, yeah, more so. I mean, not totally. More so. Okay, do this one. Wait a minute. Time out. Go back to this. Remember how we said that any sigma, if you shift this I, we can adjust what was in here, and so there's really an infinite number of sigmas that we could make work that would represent the same thing, right? Right? Now, let's say somebody else thought on this one to write that as sine of 2, which actually Max did a little bit, right? Let's say you had written it this way. Right? With me? Now, when you plug in your 1, you get 2 plus 5/100. Then you get 2 plus 10/100. So you get 2 plus 3/100, right? You're moving over, or no, I'm sorry. You get 2 plus 5/100, 2 plus 10/100, 2 plus 15/100, right? You're moving over 5/100. What if somebody wanted to, instead of circling that as the German shorthand, the thing that's changing every time, because it is, that's right. Couldn't I do that as my x? Couldn't this function have been sine of 2 plus x? Now, right, now think about this. So if that's the case, I don't like doing it this way, but sometimes people do, and sometimes there's a reason why you may think this way. If I put I of 100 in here, So now if this is what I'm calling my X, right? This is the part so now this becomes this part here, right? So now when I put a 1 in, I got 5 100ths. The very first thing I plug in, remember, this is where I'm plugging in now. So the very first thing I plug in is 5 100ths. And then the next thing is 10 100ths. What's my left edge been? If the very first thing I plug in is 5 100ths, must have been 0, right? So in that case, if this is my X, in this case, this would start at 0 and then go where? Now you tell me, are these two the same area? Because what is this graph right here? And that's, Max, what you were just saying. It's this graph shifted 2 to the left. Well, if you take this graph and shift it 2 to the left, wouldn't the area from 0 to 5 be the same as the area from 2 to 7? Right? I mean, here's the sine graph. And 2 to 7, is what? Wherever it is. If you take this graph, so let's say it was here, 2 to, let's say 7's out here. Right? So whatever that area is, if you take that whole graph and shift it left 2, isn't that area now, instead of from 2 to 7, isn't it from 0 to 5? So it doesn't make sense. If there's an infinite number of sigmas we could write for a certain area, isn't there really an infinite number of integrals we could write as well? And we could make our integrals always start at 0 just by shifting them, right? I'm not saying you want to do that. I'm just saying that's a possibility. Now, why did I do that? Because you guys are really getting the hang of it. You say, well, way to go. Now you just confused me. Okay, well, in the packet, remember that multiple choice problem I showed you the other day? See, when you're doing in the EP test, you're doing a multiple choice. You might work out this sigma and come up with this, but they don't have that as one of your choices. They have this as one of your choices. See what I mean? So you've got to understand that this is the same as that, right? So that's the only time you'd have to do it. So to be honest, you could still work it out your normal way, the way we've been working it, right? The way we've been doing these two. You could still work that out and get this. And that would be fine. And then you look at your answers and you say, oh, geez, that's not in there. But there are some that are shifted. So now I can just shift it and find them, right? And so you can do it that way. All right. Do this one. Emily got it? Will got it? Max got it? Well, what's harder about this one?
Is it in,
The ands? Well, here's the thing. If your width is 3 100ths,
the midpoint, it's total width is 3,
okay, if your width is 3 100ths, the next one is 6 100ths, the next one is 9 100ths, right? So if your width is 3 over n, then your next width is 6 over n, and your next width is 9 over n. That didn't change, right? And what would be a midpoint on 3 over 3 100ths? This would be 6 over 200, right? This would be 12 over 200, right? So 6 over 200, 12 over 200, so in between there would be 9 over 200, right? So what's in between here? So what's this? So 3 over n is the same as 6 over 2n, and this is the same as 12 over 2n, and so halfway between there is 9 over 2n. You see what I mean? So it's the same thing, right? If there's n's, it's the same thing as 100s or 10s or whatever, right? It's really no different. What is the difference here? I mean, obviously there's n's, but what is the other difference?
There's no one odd on the side of your x. So all our x's have been equal or something.
Yeah, but isn't this just split apart? Didn't I just split this apart? Right? Like this one, like you were saying, Matt, couldn't you just do that? This is just 2 plus 5 over 100. So isn't that what happened here? It just got split apart. So I think a big hint there is the left edge is 3, just like we talked about here. This would have been 2 plus 5 100ths. That's a big hint that left edge is 2. It's not automatic, but usually that's what that means when it's split apart like that. Okay? Now, what's the other thing? But remember when I asked you, are these two the same? No. Because this is what? This was 10 left rectangles. What was this? 100 right rectangles. So it's closer, but it's not the same, right? What is this? How many? But they're midpoint rectangles. I agree. As soon as I see that 2n and that n, they're midpoints, right? How many are there? Infinite. So the integral rewrite? We could literally write equals in between, right? On these two, we would have to say approximate, right? These are approximate to each other, right? The integral I'm about to write, I could literally put an equal sign in between, right? Not on these two, because they're not the same. It's an approximation. But that's the only difference. So I don't care about this limit. I mean, I care about it in the sense that tells me I have an infinite number of them. But as far as how I write this integral, that's not a factor. All I need are the things you guys talked about before. So, what do you think your function is? Let's do that. That's the easy part. Just e to the x, right? E to the messy stuff, right? All the messy stuff's where the x goes. The width, the 3 over n, just becomes the x, right? So easy. And then where do we think it starts? We think it starts at 3 because of that. But what did we say? We said let's plug a 1 in, right? So let's plug a 1 in. So we plug a 1 in. We get 2 minus 1 is 1. Times 3 is 3. So we get 3 plus 3 over 2n. Now, what did we just say? What was the width? 3 over n, right? So if this is 0 over here, 3 over n, halfway between there is going to be 3 over 2n, right? Because the 3 over n is 6 over 2n, so halfway is 3, oops, that's not 3n, there's 3 over 2n. So 3 plus 3 over 2n, isn't that half a width? 3 over 2n is half a width. So 3 plus 3 over 2n should be my first midpoint, right? 3 over 2n is half a width. So where's my left edge again? Say it again. Doesn't that all lead to telling me the left edge must be 3? Right? The left edge must be 3. Because if I plug a 1 in for k, I get 3 plus 3 over 2n. Well, 3 over 2n is half a width. And that's what a midpoint should do. It should go over half a width. Okay? And then what gives me this number? Yes, I could put my n in here. Now that would get messy. So that's probably not my preferred choice. I would rather say, well, if my width is 3 over n, and we have how many rectangles? N. If you go from 1 to n, what's 3 over n times n? So total width is 3, so this has to go from 3 to 6. Or my other version that we just talked about could have been, this could have been e to the 3 plus, right? This messy stuff could have been my x, but that's just e to the x shifted over 3. So instead of 3 to 6, it would be 0 to 3. But again,
I wouldn't worry about that. But if it was a multiple choice problem and you had to, to do it. Or, on the quiz, I could do a true false. I could say, is this the same as this? Right? And you would have to but maybe you go through it your normal way, write it like this, and then say, yeah, are those the same? Oh yeah, it's just shifted left. 3. Okay? So that one was trickier because I put in the ends and I made it a midpoint. So both those things added a little difficulty to it. But remember, if it starts at 3 over 2n is half a width. Understand that. You just double the bottom number. That's how you take half of something, right? You multiply something times a half, what are you going to do? Right? You're going to take the bottom number times 2. Right? So you take half of something, then you're going to double the bottom number. So when you see 3 over 2n, that's half a width. Well, that's what a midpoint rectangle should do. It should go over half a width. All right. So a lot of your homework is going to be doing this right here. Okay? All right. So let's go on section, so this is in that 5.7 where we were before. Let's go 27 through 33, which is, now, this is a little bit unfortunate because here's what they do in the book. They do this. They say, show that this is equal to this. So they've already given you the answer, which drives me nuts. I wish they hadn't done that. So, I don't know what to tell you. There's not a whole lot to do on that one other than if it were me, I would cover up. When I was doing the problem, I would just cover this up with my hand and see if I could figure it out. Put my paper over it and see, if I can get that. Okay? So that's what you got on that part. And then, hang on here, 39 through 42. Now, in 39 through 42, they don't do that. So those are some sigmas you actually have to be able to figure out the integral. And then 45 and 46. Okay? So 27 through 33, they give you the sigma, but, cover up that integral with your hand, with your paper, with something, and see if you could make sure you could get it.
What do you want us to write down for 27?
The integral that they already give you, but that's what I'm saying. Cover it up. Cover up the equals. It says sigma equals this, show that. I want you to get the integral. But yeah, so could you just copy down what they say there? Yeah.
Well, on 27 and 28,
I know. Well, it's the same. Now, what would be good is to explain the difference, right, between the two sigmas. I mean, make sure you understand what's different about those two sigmas.
your second block, students have first off?
No, there's a lot of music.
Is that
Some of them may. There were some that had, Joe,
Yeah, finishing some.
there were some that had like physics, I think, in the fall, so it conflicted with the second block. Yeah, I definitely think there's some that could have probably switched at semester, but then they may have then went to a block off, seniors.
Physics is
Have you guys decided on hiring a math teacher?
Yeah, we've had a couple.
what they gonna teach.
I don't know. We haven't figured that out.
Because they definitely need more science teachers.
Yeah, I think they've hired those two. Yeah, because Mr. Lindeman and Willer
Yeah.
are leaving. Should retire.
Is he doing that so he can do it?
I don't know.
Yeah, does he do research? He's cool.
How's that right? Yeah,
It's like all
we've
of our
hired,
science
we got two
department.
math teachers, two new math teachers.
Are they like both younger?
Yeah. Yeah, one's taught a couple of years, one's been teaching 10.
That's like all of our science information on in the past 2 years.
So, she's retiring. I don't think so.
After next year.
Yeah, I don't think she's retiring this year.
She said she's going there, she's going.
So we'll get a decamp.
This was, yes.
Eating.
Oh, I could probably quit recording.